Okay, now classification of reactions, you'll have to pardon some of the background noises, get some people working on labs, so don't worry about that. If you hear like water pouring and just glassware clanking, it's all good, don't worry about it. It's okay, you can have lab noises. I was telling the person who was like freaking out, so don't worry about that. Okay, classification of reactions is something I've been sneaking in with this chapter all along, so this shouldn't be terribly new. We've already covered double displacement reactions. There's two types of double displacement reactions. It's either a precipitation reaction or it's going to be an acid-base reaction. Then the new things we're going to talk about in this video are the oxidation reduction reactions, or like I like to call them, redox reactions. So there's four types of redox reactions. They're called single replacement or displacement, combustion, which I've already snuck in on you, decomposition, and synthesis. Now I know I've stressed double displacement reactions quite a bit so far in this chapter, and a double displacement reaction uses as reactants two ionic compounds, and then at the products we end up with two ionic compounds, and basically it's just an anion swap. So it would look like this for those of you who are fairly visual. But if we were to actually use cations and anions, I like to go through and write the charges. So I know the sodium ion has a +1, sulfate is -2, lead for this one is +2, and nitrate is -1. Now I'm going to swap the ions, so sodium is going to end up with nitrate. Now I don't have enough room to put this all in one line, so I'm going to drop it down here, Na, NO3, plus, now lead's going to hook up with sulfate, PbSO4, and according to the solubility rules, that forms a precipitate. Now we just need to balance it. So we have two nitrates there, so I need two sodiums. We have two sodiums. Oh, we're good. Now acid-base reactions are also double displacement reactions because an acid is an ionic compound. Well, a strong acid anyway is an ionic compound, and a strong base is also an ionic compound. So over here I'm going to go ahead and write my charges. SO4 would be 2 negative, potassium plus, and hydroxide negative. So hydrogen's going to hook up with hydroxide, and I like to leave it as HOH until it's balanced. And then I'll put it back to the water the way it should be. Only if you ask me, I should leave it as HOH, but you know, nobody asks. So then we have K2SO4, and we need to balance it. Here I have 2, so I need 2, which means I need 2 hydroxides, so a 2. This says 2 hydrogens, which I have. So we're balanced. So I'm going to change the HOH to be H2O, because that's the way it should be. So we're going to make it H2O, because by convention, H2O is the proper way to write it. But if you'd left it HOH, I would have let you have it. Okay, that covered our two types of double displacement reactions. We either have a precipitate reaction or we have an acid-base reaction, and we've already covered those, so those should be easy peasy to identify and label. Oxidation reduction reactions we're going to cover shortly. We have single replacement, that'll be the first one I talk about, combustion, which I've already talked about, decomposition, and then I'll talk about synthesis. These are all redox reactions. And if you recall, in a redox reaction, electrons are transferred. That is the key to recognizing a redox reaction. We're going to start off with combustion. Yay! A combustion reaction has to have oxygen, because if you don't have oxygen, nothing will burn. See, for instance, if you put a lid over a candle, the flame goes out because there is no oxygen. So you have to have oxygen, and it produces energy. Wow, you get so much energy. You know, your car works off a combustion engine because the octane combusts to give you the energy, and your homes are heated by a combustion reaction, whether you have a big tank in your yard or you don't. Most of us are still using some sort of combustion reaction to get heat energy. This would be a basic example. So you have, and for this class, most of the time, like 99% of the time, I'm going to use some sort of carbon-based substance, whether this is called a hydrocarbon And a hydrocarbon, like the name suggests, has a hydrogen in it and a carbon in it. See, like the one below. Or I'll use a carbonate. Well, I should call it a hydrocarbonate. So a hydrocarbonate is going to have hydrogen, and it's going to have a carbon, and 8 means oxygen. See, glucose, C6H12O6. That is a hydrocarbonate. And either one of those will typically be what I use for a combustion reaction. You'll always have oxygen as a reactant because no oxygen, no burn. Now the really cool part about this is your products are always going to be the same. If you burn a carbon-based substance, you will always get out carbon dioxide and water. Always. Those will always be your products. If you recall, to balance these, first you look at the carbons. Oh, they're good. Then you look at the hydrogens. Well, I'm going to need 2. Now you look at the oxygens. 2 oxygens and 2 makes 4. 2, we are balanced. Okay, now that we've talked about double displacement reactions, we talked about one type of redox reaction, that was combustion. Now we're ready to talk about single replacement reactions, or you could call it single displacement. Either way is fine. Okay, single replacement reactions are very similar to double displacement reactions, but instead of involving a swapping of 2 anions, you're only going to swap out 1 anion. It's kind of like high school. See, A was alone, but A was thinking C looked really hot, and so it made up this big rumor and got B and C to break up, and now B is all alone and A and C is together. See? Single replacement reaction. Or if you prefer a picture, see, red and blue were together, and yellow really thought, which one do you think yellow would be interested in? The blue one or the red one? Well, it's got to be the blue one, because to have an ionic compound, you have to have opposite charges. So then yellow goes and makes up this big rumor, and red and blue split apart. And now yellow has blue, and red is left all alone. Another example would be this. Now, I will be requiring you to be able to predict the products in a single replacement reaction. So to predict the products in a single replacement reaction, I like to go through and write the charges off to the side. So we know potassium as an ion will be a plus charge. And copper as an ion, well, we'd have to figure that one out. But nitrate is always going to be -1. So if we look at this half of the ionic compound, nitrate is going to be -2, because -1 times 2 is -2, so that means copper has to be +2. Well, since potassium is now going to be left alone, we end up with potassium, no charge, becomes, oh, I said that wrong, sorry. Potassium is now going to hook up with nitrate. So we have KNO3 plus, now copper is going to be the one that's going to be left alone, so it goes from being an ion to being just the copper metal. Now the last step is to balance it. So we have 2 nitrates, so I need 2, which gave us 2 potassium, so 2, and we are done. All right, the next type of redox reaction we're going to discuss will be synthesis. Synthesis means to put together. A synthesis reaction is where you take many and you make it into one. That's one way to think of it, many into one product. But that doesn't quite tell the complete story, because by many I mean elements. Elements go into some sort of ionic compound. In other words, electrons are transferred. Anytime you have electron transfer, you're going to have a redox reaction, and this one's called synthesis, and you will always have one product. So here we have the element red and the element blue, and it makes the ionic compound. Another way to look at it is this reaction. Here we have carbon with an oxidation number of 0, oxygen with an oxidation number of 0, but this compound, okay, so it's not always ionic. We could also have ionic or covalent, but some sort of compound. And here, Electrons had to transfer to make this compound or this molecule. See, oxygen has an oxidation number of -2. We have 2 of them, so carbon must have an oxidation number of +4. In order to go from 0 to 4, electrons were lost. So that means carbon was oxidized. I know, it's a bad word, oxidized. I don't know why electron lost is called oxidized. It just is. I mean, I'm sure there's a good rational reason. That's what we stuck with. Now, oxygen went from 0 to -2. So this one was reduced because it gained electrons. Its charge went down. And that one actually kind of makes sense to me, even though at first I know it seemed like, what? But no, it makes sense. As you can see, this is a redox reaction. Somebody gained, somebody lost, and it is synthesis because one thing was made from its elements. The last type of redox reaction I'm going to talk about now is decomposition. And decomposition is the opposite of synthesis. See, in a decomposition, we're always going to start off with one reactant. Oh, I'm going to change my pen color here. One reactant, one. And it's reactant. And it's going to break down into many different things. Now, a better way to put this is we have some sort of compound, as I illustrated in the last slide. When I tell you about synthesis, it could be ionic or covalent. It doesn't matter. And it's going to go to its elements. That's crucial. Because it's a redox reaction, electrons are going to be transferred. This is a nice visual for decomposition, but let's take a look at this particular formula here, this reaction, I should say. In this particular chemical equation, I had to figure out where it was because I paused and answered a question. Okay, so in this one we have water, single reactant. And it's going to break down to its elements, hydrogen and oxygen. Now, it's decomposition, which is a redox reaction. The reason it's a redox reaction is, well, if we look at the oxidation numbers of everything involved, oxygen is -2, hydrogen is +1. Here, hydrogen is 0 because it's an element, and oxygen is 0. So take a look at hydrogen. It went from a +1 to a 0. It was reduced. It had to gain electrons. That means oxygen, which went from a -2 to a 0, had to lose electrons. So it was oxidized. Look, it's a redox reaction. And the type of redox? Decomposition. Take a minute and see if you can classify these two reactions. Pause the video and then restart and see how you did. This one is a redox reaction. It is redox, well, because this is 0 and this is an oxidation number of 0, +1 and -1. Oh, so electrons had to be transferred. Or you could recognize this reaction as a synthesis reaction, and synthesis reactions are always going to be a redox reaction. This particular reaction, we have an ionic compound, a single person, an ionic compound, and a new single person. Well, this one happens to be single replacement or displacement, it doesn't matter. But it's also a redox reaction. And the reason it's redox, well, take a look at aluminum. Here, what is the oxidation number on aluminum? Well, it's 0. What's the oxidation number on the ion? It's +3. Well, that means electrons had to be transferred in order to make that happen. Or look at the iron. Iron here would have an oxidation number of +3, and over here, it's 0. Oh, it's not +3. Brain engaged, sorry. It's +2. Well, what that means is electrons had to be transferred. Therefore, it's redox. The type of redox? Single replacement. Once again, you try classifying these reactions and push play and see how you did. This A is a redox reaction. You can look at the oxidation numbers and see that clearly the oxidation numbers have changed. So if they changed, that means redox. Electrons were transferred. What type of redox is this? It is synthesis. Elements to 1. What about B? What did you say for B? It is definitely double displacement. What type of double displacement? Well, that means we need to look at these guys. This one's an acid. It's one of the strong acids I said you need to know. This one's a base. It's the same base you used in your lab. Ooh, we made water and a salt. Therefore, it is also acid-base. Take a look at this one. Pause the video again, see how you do. Don't just blindly write them down. Okay, so let's see. Now that you've restarted the video, what did you say A was? Well, it is double displacement. We have ionic compounds everywhere, but what kind of double displacement is it? It is a precipitate reaction. Oh, look, there's your precipitate right there. And B, what kind of reaction is it? Well, let's see. This has zeros for oxidation numbers. Lead is a +2, oxygen's -2, so that means it's redox. What type of redox is it? It is decomposition. Something broke down. You can try these next several slides on your own and bring them to me, see how you did. I'd be happy to take care of those for you, for the extra points, I mean. In conclusion, then, you need to be able to classify chemical reactions. The first type is double displacement. There are 2 types of double displacement reactions. It will either be a precipitate reaction or it'll be an acid-base reaction. The second type of classification that you would have to recognize is redox, and this is where electrons are transferred. There are 4 types of redox reactions that you should be able to recognize: single replacement or displacement, combustion, decomposition, and the opposite of decomposition, synthesis. Up next, we will start one of my favorite topics, stoichiometry.